In this work, we present a score distillation framework for constructing reusable, modular motion priors that enable physically simulated agents to perform a wide range of tasks with natural, lifelike behaviors. Score distillation sampling techniques have been a powerful approach for constructing image-based generative priors, supporting a wide range of applications including 3D and 4D asset generation. However, when applied to control problems in a reinforcement learning framework, policies trained with SDS-based objectives often produce low-quality results. The quality of the resulting motions falls far short of what has been achieved with adversarial priors. Adversarial motion priors enable lifelike behaviors by training a discriminator in tandem with a policy. However, this results in a highly specialized reward model that is tightly coupled to a specific policy. Furthermore, the discriminator must be continuously trained using the motion dataset. Therefore, a discriminator trained with one policy cannot be easily reused to train new policies. In this work, we propose SMP, a score matching method for creating reusable and modular motion priors. The motion prior is represented by a motion diffusion model, trained independently of any task or policy. Once trained, the prior remains fixed, and acts as a motion-style reward that provides a robust measure of how closely the agent's motion aligns with behaviors in the reference dataset. This similarity measure is computed using the SDS error. We begin by adding noise to the agent's motion, and then the pre-trained diffusion model is used to predict the corresponding noise. This prediction indicates how the noisy sample should be denoised toward the reference distribution. When the agent's motion closely matches the behaviors in the reference dataset, the difference between the added and predicted noise becomes small. This noise prediction error is then used as a reward signal for training control policies. The motion reward model built from SMP can be reused and combined with different task objectives to train policies in a reinforcement learning framework. We incorporate several key design choices that improve the stability and effectiveness of policy training with SMP, enabling agents to learn high-quality, naturalistic human behaviors. We first train an unconditional diffusion model on an unstructured locomotion dataset. This pre-trained locomotion prior can then be used to train policies that produce human-like locomotion behaviors across a diverse array of tasks. The steering policy automatically transitions between different locomotion gates depending on the specified command, without the need for an explicit motion planner. Policies trained with SMP exhibit human-like strategies. Here, the character automatically slows down as it approaches the target. When the target is far away, the character transitions to a fast-running behavior. These nuanced behaviors arise automatically by training with the motion prior. SMP provides the policy with the flexibility to adapt behaviors in the dataset in order to create new skills for different tasks. In this dodgeball task, the character develops highly agile behaviors to dodge incoming balls, such as jumping and dodging. These behaviors were not present in the original dataset, but they closely resemble real human strategies in dodgeball. What if the character gets knocked down? It can also learn to recover naturally with a get-up prior. SMP can also train a general motion prior on more than 20 hours of motions across 100 different styles. This prior can then be reshaped into style-specific priors that encourage different stylistic behaviors, ranging from twirl steps to high knees drills and zombie walking. SMP can be used to train policies for these diverse behaviors without requiring access to the original dataset. Furthermore, we can use SMP to create new motion styles without data by blending the predictions from different styles. Here we blend the priors for the high knees and aeroplane style, and the agent learns to move towards the target with arms spread wide, and knees lifted high. Let's have some fun with style composition. Elated? Not energetic enough. By blending exaggerated arm swings with flicking leg motions, we create a lively and humorous new style. We can even teach the character basic ballroom dance elements, holding one arm across the chest, extending the other, and spinning smoothly through space. Our framework can also train priors for human-object interactions. By training a diffusion model that jointly models human and object motions, we can train policies for interaction tasks. The character learns to walk to a box, pick it up, and carry it to any target location, all with natural, coordinated, and physically plausible movements. With a simple human scene interaction prior for staircases, SMP enables the character to climb up and down stairs with natural motions. Like other distribution matching methods, our approach can learn from as little as 3 seconds of motions, while still allowing the agent to adapt transitions and behaviors beyond the reference data. In this example, the dataset contains only 3 motion clips that move at different speeds. But the policy then learns to adapt those motions to move at a wide range of target speeds. SMP produces high-quality motions, comparable to those generated by state-of-the-art adversarial methods. SMP can be used to train controllers for real-world humanoid robots. The robot demonstrates robust locomotion under external perturbations, exhibits safe and smooth behavior when grasped and pulled, and automatically adjusts its stride to maintain balance and continue moving forward when struck by a mat. These behaviors emerge without relying on a real-time motion planner or manually designed heuristics. More details are available in the paper. Thanks for watching.